Right, welcome everybody. I forgot to turn on recording in class, so upon some request, I'm re-recording some select concepts about SRAM to make sure that you could still listen to them at home in case you missed the class. So I will start with the regenerative property of CMOS inverter. As we discussed briefly in the class before this lecture, that if you have a chain of inverters driving each other, uh, they exhibit a property called regeneration, meaning if for some reason one of the node voltages degrade beyond 0 and VDD, for example, if you have 0 to VDD, that's the most ideal rail to rail swing. But in case maybe one node voltage is less than VDD for some reason, maybe because of noise, because of other degradation, interconnect driven degradation, for a chain of inverter, they can quickly get over this degradation and get to a level which is appropriate VDD. Let's take some number. Imagine your VDD is, give me 1 second. Imagine your VDD is 0.9 volt. Okay. So if you provide 0.9 volt at this node V0, you should get 0 at the output. And for 0 as the input for the second inverter, the output should again be 0.9 volt, and so on, right? Now, instead of 0.9 volt, if you provide 0.7 volt as an input to this inverter, the regenerative property ensures that at some point within these internal nodes, you will get back 0.9 volt as the node voltage. So let's take some numbers here. So what is half of 0.9 volt? 0.45, right? So ideally, anything above VDD over 2 should be treated as high voltage. So 0.7 volt will be treated as high voltage, obviously. So this inverter will create 0 at the output, and the next inverter will hopefully create 0.9 volt as the output of second stage. And then the next stage will keep doing as if everything is regular, right? So this degradation of voltage will not really affect the chain of inverter performance unless it's beyond a certain limit. And this diagram shows you exactly what I just mentioned here. So imagine this is V0, which is the first input. And imagine our VDD is 5 volt for this particular example. So you are dealing with 3 volt here. That means there has been a degradation. Instead of 5 volt, you're providing 3 volt as input, right? I hope you see that here. So since you are applying 3 volt, the output should still be 0 because 3 volt is greater than 2.5 volt, which is VDD over 2. So now if that's the case, after 0, the next level should have 5 volt and so on. Let's see whether that's the case here. Notice what is V1. When you provide 3 volt, the output, which is V1, can still become very close to 0 volt, not exactly 0, but very close to 0. But then V2, let's see what happens to V2. V2 becomes almost perfectly VDD. And it gets back to the rail to rail swing situation. That's what regenerative property means. And I'll show you why it takes some time to get back to 0 and VDD. Why cannot it directly go back from 0 to VDD directly after one stage? It could take a couple of iterations. And the explanation comes in the next slide here. And I'll show you what, how that eventually comes to rail to rail swing. Imagine this is the voltage transfer characteristics of one inverter like this. And if you're driving an inverter with another inverter, for example, second inverter is being driven by the first one, I can consider that the output of the second inverter is basically the input of the output of the first inverter is basically the input of the second one, right? So imagine if you plot V out versus V in for inverter 1, and if you could just flip the axis, so V in will go to Y axis and V out will go to X axis, you get the voltage transfer characteristics for the second inverter. All you have to do is flip the curve. So for example, if Y versus X looks like this, X versus Y, if you just flip the axis, will look like this. And that's what you get here by flipping the VTC, voltage transfer characteristics of inverter 1. Okay, if you flip it, you get the same characteristics for inverter 2. And this diagram is called a butterfly curve for inverters. They're very helpful in determining many properties of inverters. So this is your first voltage transfer characteristics of one of the inverters. And the second one will have these voltage transfer characteristics. All right, so let's start with the first one, which is this one. Imagine you apply a voltage V0, which is less than VDD over 2. This is your VDD over 2. So this should still be treated as a low voltage. And we should expect to get a high output, right? Let me mark VDD over 2 properly. This is VDD over 2, this is VDD over 2. VDD over 2 and VDD over 2. All right, now let's consider that you apply a voltage V0. Maybe you wanted to apply 0, but for some reason, some sort of aberration, external noise, it ended up being higher than 0. Okay? Now, how can I find out the output corresponding to this one? So remember, in the y-axis, you have V out. In the x-axis, you have V in. So for this input, I can easily find the output by looking at the VTC, this voltage transfer characteristics. And this is going to be my output. See, it's not VDD yet, right? That's the reason why you don't really get back VDD right after the first inverter. But notice it's still above VDD over 2. So it should be treated as a high voltage. So it's doing the right thing. It's giving you high voltage corresponding to low input, but it's not giving you high enough voltage. It's not VDD yet, right? We want to get to that point. So let's see what happens to the next inverter. So all we have done so far is looked at the input of the first inverter and output of the first inverter. Now, the output of the first inverter should be the input of the second inverter, and we'll have to look at the output of the second inverter now. Okay, so let's do that. Let me erase this section. Oh, okay, let me erase this section and see how we can find out the output for the second inverter. Notice the input of the second inverter will be in this axis, right? Clear it up completely. This is basically the input axis for the second inverter, and the output axis of the second inverter will be practically the x-axis. So this is the input for the second inverter. Corresponding to this input, how can I find the output? Which VTC should I look at? Should I look at this VTC or the other VTC? Remember, I just told you, this is the voltage transfer characteristics of the second inverter. So we should be looking at this one. So corresponding to this input, V1, this is my output. Notice, this is supposed to be a high input. For high input, we should expect to get low output. And notice, this output is very close to 0. So it's getting better, increasingly better. Now, if you do one more round, so this will be, imagine if you have 3 inverters back to back, 1, 2, 3. For the third inverter, you get back to the first VTC. So all the odd placed inverters will be having the same VTC. Number 1, number 3, number 5 will have a VTC like this. And all the even placed inverter will have this kind of a VTC. Number 2, number 4, number 6. So imagine now we are dealing with number 3 inverter. So for that, this will be our input. And this will be our VTC. So for that inverter, our output will be, there you go. You see that? It's pretty much almost VDD. So it took about 3 inverters to eventually get back to VDD completely. And then after that, you'll be just dealing with 0 and VDD all the time. Rail to rail swing, 0 and VDD. So it took 3 inverter or 3 stages for you to completely get back to VDD because your input was so bad. Apparently, it was almost close to VDD over 2. But if you have a smaller aberration, smaller degradation, then it will probably not take 3 inverters. Maybe 2 will be just fine. But that depends on multiple things. How good are individual inverters, how much gain you have in them, and other properties of the inverters. But you get the point. Inverter change will always regenerate the degraded voltages. That's a very big advantage of using CMOS inverter. Just to quickly show you, in situations like this, where, let me just go back to the drawing board. If your VTC looks like this, output versus input, you have regenerative property. But if your VTC looks like this, you do not have regenerative property. Okay, and there are situations where this VTC could degrade gradually and become like the one that I showed you. And that means a CMOS inverter could lose its regenerative property if its VTC degrades. And one of the ways to degrade the VTC would be to reduce VDD. If you keep reducing the VDD of an inverter, let me show you. I have a few slides about it later. For one VDD, imagine this is 1 volt, 1 volt. This is your VTC. If you reduce the if you reduce the VDD to say half volt, 0.8 volt, say 0.8 volt, 0.8 volt, your VTC changes. And if you keep reducing it too much, at some point, you'll see that it will flip. So the VTC will become like this, degraded. And that means the inverter will lose its regenerative power, okay? Just so you know. And basically, you could do the same exercise, considering this to be the first VTC and the flip version of it to be the second VTC, and go through the same exercise, and you'll see you will never get back to regenerative property. I'll show you. Maybe this is your V0, a degraded voltage. And for the first inverter, you should look at this VTC. For 0 input or low input, you should expect high output. And let's see, you get an output like this, V1. Now, keeping this as the input for the second inverter, I should look at the other VTC to find out its output. Let's see where the output is. The output is somewhere in the middle. Wow, this was supposed to be a high input, and for that I was supposed to get a low output, but it's actually not improving. It's getting, worse eventually. V0, I started with a voltage that was slightly higher than 0. Now I have a voltage which is even higher than 0, which is basically not improving. It's, if anything, it's degrading it further. So that's what I mean by not having a regenerative property, okay? Keeping that in mind, back to the SRAM, we, in an SRAM cell, like I said before, we have 2 back-to-back inverters, one driving the other. You could consider this to be like an infinite chain, one inverter driving the other, and this one driving this one. And so basically, inverter number 1, if it has a VTC like this, inverter number 2 will have a VTC like this. So you have a butterfly curve, and inverter 2 will drive inverter 1 again, and inverter 1 will drive inverter 2 again. So the regenerative property that I told you about, it helps with storing information at these storage nodes. If one of these nodes is set somehow to VDD, the output of this inverter will be 0. And since this is 0, this will be the input of the second inverter, whose output should also be VDD. So basically, they will maintain each other. If for some reason this VDD degrades below the level you want, say VDD minus delta V, the output should still be 0 as long as it is not too much. And then the other inverter will change this node back to VDD again. So they will regenerate any degradation. If for some reason this 0 increases to some value, like say delta V, this inverter action should change it back to proper 0 again through regenerative property. That's what I'm saying. So that's how the chain of inverter or cross-coupled inverter maintain the storage node voltages despite some sort of noise input or some other aberration. That's why we use cross-coupled inverter in an SRAM cell. Okay, so the other two transistors that you see here, they are used to access the storage nodes. Can you write into the storage node? Can you read from the storage node? Yes, using these 2 transistors. They are called access transistors because they help us access the storage node. And if you kind of draw the full circuit form of these 2 inverter, that's what you get. 2 transistors here, 2 transistors there. And notice the output of this inverter is connected to the input of the second one. And the output of this inverter is connected to the input of the other one. So basically, this is what you get here. It's more complicated, but it shows you the full picture. And then these are 2 access transistors. Let's talk about how to read and write from SRAM cells. When you read, we use 2. Let me just use a different color here because otherwise it will not be visible. Remember, I told you that in an SRAM, you have access transistors, and the access transistor gates are connected to a line called word line. And these word lines are shared across the row. So there will be SRAM cells, say SRAM, connected across the row, like along the row. And there will be SRAM cells in every column as well. And the SRAMs in one column will have two bit lines, bit line and bit line bar. So basically they will share the bit lines and bit line bars, and similar for the other ones as well. So now when you read, so at every SRAM cell, you have two bit line and bit line bar, and one word line. When you read, you first activate the word line, meaning by activating, I mean provide VDD or the supply voltage to the word line to turn on these two transistors. Okay, these two transistors. Okay, after that, you pre-charge your bit line and bit line bar, these two lines, to VDD over to VDD. So basically pre-charge both of them to VDD. Okay, and remember, when I say pre-charge, there is a difference between pre-charging and driving. Notice that I said we pre-charge the bit line. I didn't say we drive the bit line. When I say drive, you use a separate circuit to keep that voltage constant, and you replenish any changes that takes place. But when I say pre-charge, you basically take the voltage to that level and let it go. This could further increase or decrease depending on the environment, depending on the interaction between other transistors and the interconnect node. Okay, so that's the difference. So during read, you start with pre-charged VDD. The question is, where will this charge be stored? As I explained in the class, that when you create any interconnect, any line in a actual hardware, you have capacitor built into the line. Every interconnect line will have capacitor built in. So the capacitor that's there, it's built into the interconnect itself. You don't have to connect a separate capacitor. It's part of the bit line. It's part of the bit line bar. So that's where the charge is stored. Okay, so imagine you store VDD. Let me use this diagram instead. It has all the transistors. So VDD and VDD. And remember, these transistors were activated. Now, considering that you have a situation where this node was storing VDD and this node had 0. Okay, so then let's find out which of these transistors are active. Okay, if this is VDD, this node will also have VDD. That means this transistor will be active. NMOS will be on when you have a VDD as gate input, right? But the PMOS will be off for the same gate input. On the other hand, if you have 0 at this node, this PMOS will turn on, because PMOS's turn on will opposite voltages, as you know, but the NMOS will turn off. And that's what you see here in this simplified circuit. But by the way, this circuit considers the opposite. It considers that storage, this node was storing 0 and the other node was storing 1. Well, let me do that actually to avoid any kind of confusion. So let's consider that this node was storing 0 and this node was storing VDD. If this is 0, then this NMOS will be off, but the PMOS will be on. This PMOS will be on. And if this is VDD, then this NMOS will be on, but the PMOS will be off. Okay, so that's what you see here. And that's why the rest of the circuit been omitted to ensure simplicity. But now, since this node was storing 0 and this node has VDD, this bit line will try to charge up this storage node further. Okay, so basically this will go from 0 to some voltage, Vx. Okay, in doing so, the bit line will lose some voltage, Vx, VDD minus Vx. On the other hand, since this node was storing VDD, and for this case, 1 represents VDD, as you know, this logical 1 represents VDD. So, and your bit line was also VDD, so there is no voltage difference between them. There will not be any charge or discharge here. So this bit line voltage will hopefully remain at VDD, and the other one will the other one will go down from VDD minus Vx. So if you have a sense amplifier connected to this two bit lines, it can sense the difference. It can sense that one of the bit lines voltages went down. So if this goes down, then you all immediately know that this node was storing 0. On the other hand, if this node was storing VDD and this other node was storing 0, and you connect these 2 bit lines to a sense amplifier, then this bit line voltage will go down. So you have VDD minus VX here and VDD on the other side. That's how you know that this node was storing 1. Okay, I hope that makes sense. So it's a very easy read operation, and by the biggest advantage is that you can use these 2 bit lines to sense. You don't have to create a separate reference. This is called differential read. So basically, these 2 bit lines help you generate the reference in there. They are self-referencing per se. You know, there are different ways to put it, but you could call it differential reading or self-referenced reading. The good thing about differential reading is that they are immune to noise. They tend to be more resilient to noise input, because if you provide a noise, let's consider a situation where both of these are connected to the bit line, sorry, the sense amplifier, and maybe this node was storing 0 and this node was storing VDD. That means this bit line will go down from VDD minus delta V, and this node, this bit line will stay at VDD. Okay. Now imagine you somehow have a noise injected somewhere, and since they are close to each other, they will hopefully be affected similarly. So there will be a noise injection, V noise, added to both sides. And since this is added to both sides, there will be, this noise will be treated as common mode noise, and the sense amplifier will completely get rid of that and help you just sense as normal. So that's the biggest advantage of having differential reading. And that's the reason why we use bitline and bitline bar both in an SRAM. One consideration that we have to keep in mind is that imagine this was 0, and when you are reading, you are charging up this node voltage. But in doing so, if this is 0, this is VDD, if you increase the voltage too much, there is a chance that the inverter will flip. Let me show you what I mean by that. Okay, so this is okay. 1 second. Okay, right. So this is an inverter. And this node was storing 0. Okay? That means the input to this inverter is 0. That means the output remains VDD. Now, when you increase this node voltage from 0 to something, Vx, there is a chance that if Vx crosses VDD over 2, then this inverter will flip and this VDD becomes 0. And if this becomes 0, this will be input to the other inverter and the output will become VDD. That means you have flipped your node voltage from 0 to VDD, which is basically a read disturb. While trying to read, you have accidentally changed the storage node voltage, which you want to avoid by all costs, right? So that means this Vx cannot cross VDD over 2, at least, if possible, even lower, right? We want to make sure that this node voltage doesn't go up too much. And how can you ensure that? That brings us to the next concept of cell ratio. Imagine when the transistors are on, they are basically like resistors, on resistance. So we're dealing with 2 resistances here, say R5 and R1, corresponding to M1 and M5. And you have a voltage at this node, VDD. And this node voltage is something that you care about. So what is Vx? Based on the resistive division rule, I should write R1 over R1 plus R5 times VDD. This is what the node voltage is. Notice if the resistance of this transistor is high, then Vx will be high. So you want to make sure that this resistance is much smaller than R5. And how can you make a transistor less resistive? You can make it less resistive by changing its width to length ratio. If you have higher W over L ratio, its resistance will go down. Okay, so apparently the ratio between the W over L ratio for number 1 and W over L ratio for number 5, the relative ratio matters in determining what this Vx would be. Okay, that relative ratio is an important parameter, which we refer to as cell ratio. As you can imagine, we want to make sure this W over L is as high as possible, so that the resistance of this transistor is as low as possible. That means, the cell ratio should be higher. The higher the cell ratio, the better it is in terms of read performance. Okay, and this graph shows you that as you increase your cell ratio, voltage rise of node storing 0, which is this node. Basically, this is another way of saying this is Vx, another way of plotting Vx, just Vx. Okay, the lower the Vx is, you need to create a voltage somewhat, otherwise you cannot sense. But this voltage cannot be too much, because then you'll have a read disturb, right? So notice your Vx, this is essentially Vx in the y-axis, reduces with cell ratio, with higher cell ratio, right? Which is good. You still have non-zero Vx here. This is not 0, so you can sense, but it's not too much. So you're safe in terms of reading. So the higher the cell ratio is, the better it is, as you see. So this is one important parameter. We'll have a similar parameter for the write operation, which we will discuss in the next class. So this will be the end of the discussion I wanted to record again. Thank you.